So I should sort this in this so that it's sort this in a binary tree form, I guess. So log and logarithms is bit. For that, we need to think of a binary representation of any number. Let's say our number is 101101. Okay. All right.
You told us what you want, and we built it for you. Editor X, the advanced website creation platform. Harness the combined power of limitless design.
All right, so in this video, we're going to be going over binary trees. So we're going to be covering briefly the binary tree data structure and how it's defined, and then we're going to be going over an implementation of a binary tree in Python. So for definition, a binary tree is a tree data structure in which each node has at most two children, which are referred to as the left child and right child. So here's an example image of a binary tree, and each of these circles here, these are what we call the nodes of the tree. So just like in a linked list, we had the nodes in a linked list stored some type of data. So this could be an integer, it could be a string, it could be a pointer to another data structure. In this case, these nodes contain integers. So unlike a linked list where the node pointed to the next node in the list, a binary tree has two pointers that point to its children. So every node in this tree will have at most two children, and this makes traversing such a data structure interesting and a little bit more varied than you would a linked list, and we'll get to that later in this video. So a bit more terminology about a binary tree. We refer to this top node here as the root. So in this case, the node that contains the element 2, this is the root of the tree. And then the left and right children of this root node are the nodes containing 7 and 5 respectively. So they are the left and right children of 2. So if we consider this node here, this node that contains a 7, it also has at most 2 children. So its left and right children are the nodes containing 2 and 6. And we say that 7 is a parent node with respect to 2 and 6. So 7, this node here containing 7, is the parent of the nodes containing 2 and 6. And likewise, this node here containing 2 is the parent of 7 and 5. So as we go up the tree, we go up kind of the family tree, if you like. So 2 here is the grandchild of 2. So 2 is kind of the grandparent, parent, and child. And you could keep going up the tree. We just refer to 2 as an ancestor of 2 down here. So a few more pieces of terminology here. We refer to the nodes at the very bottom of the tree as the leaves. So the root is up here and the leaves are at the very bottom. We can refer to the depth of the tree. So if we start at the top here at the root and we keep going down, we keep a count at how deep, how many levels we've traversed down. So for instance, this root here is at level, let's say you can start at 0 or 1. And then as you go down, these nodes here are at the next level. So they're at level, let's say 1, 2. And then as we go down further, these nodes 2, 6, and 9 are the next level down. So they're at depth 3. And then these nodes here, these leaves, they're at depth 4. So 1, 2, 3, 4, depth 4. Count from the bottom to the top, and that will give us the height. So if the leaves are the bottom level, let's say height level 1, then we can go up to the next level up here. These nodes are at level 2, level 3, and then level 4. So this tree has height 4. So there's different types of binary trees, and this list is not complete. There's plenty of other types of binary trees you can consider, but we can consider the 2 that we're just going to mention on this slide. So a complete binary tree. So this is an example of a complete binary tree, and a complete binary tree is one where every level except possibly the last is completely filled and all nodes in the last level are as far left as possible. So this level is completely full. You can only have one node here. This level is completely full. This node has the maximum amount of children. Both of these nodes, they have the maximum amount of children as well. And then all of the nodes in the last level with the leaves, it's not full. So we have here in the definition that possibly the last level is not completely filled. And also the last level nodes, the leaves are pushed to the far left. So this node is as far left as you can go. So in order for this to maintain the property of being a complete binary tree, the next node that we would insert would have to be the right child of this node 4, and so on and so forth. So a full binary tree is sometimes referred to as a proper or plain binary tree, and this is one where every single node has either 0 or 2 children. So every node in the tree has 2 children except for the leaves, which have 0 children. So this is full tree. Every space in this tree is being taken advantage of. So this is a full binary tree. So with that, we have enough terminology and information to start defining the data structure of a binary tree, and we're going to see a lot of overlap with what we saw when we defined the data structure of a linked list. So I would recommend that if you have not gone over that series, or if you need to brush up on linked lists, especially how they're defined, let's say in Python, to get a flavor of how we're going to extend on that, I would encourage you to go over and check out that series of videos, maybe the first couple of videos, just to get a flavor of how one would define such a data structure. And once you feel comfortable with that, we'll go over to the terminal and we'll start to define a binary tree. All right, so let's go ahead and code up our binary tree data structure. In order to do that, we'll first define a node class. So this is going to be really similar to what we did when we defined the linked list data structure, where we had a node class as well for the nodes in the linked list. So we'll say class node, and then let's go ahead and define the constructor for this class. So we'll say def init, and just like for the constructor of the node class for a linked list, it's going to take self as it's a member of this class, and also value. So this is the type of value we wish to store in this particular node. So we'll set the class variable value equal to what's passed in here. And then unlike a linked list where we had the class variable of next set equal to none, we're going to have left and right equal to none. So next that was the pointer that pointed to the next node in the linked list. Here we're going to have 2 other pointers, left and right, which are going to point to the left and right children of the given node respectively. So we'll say self.left is equal to initially none, and then self.right is equal to none. So pretty similar to what we saw in the linked list class, with the exception of those 2 last variables. Let's go ahead and define our binary tree class. So here what we're going to do is we're also going to define our constructor. So it'll take self as it's a member of the class, and also root, as that will define the tree. So we'll say self.root will be equal to node of root. So what I'm doing here is I'm assuming that a value, like let's say a string or an integer, will be passed in to define the binary tree. And then what I'm doing is I'm setting the class variable self.root equal to a node of that. So we're converting whatever data is passed in, we're storing that into a node, and we're setting that as the root of our tree here. So that's pretty much all we need to get started. We can actually start filling this tree up, although we won't be able to print anything out at the moment. So we can say tree.root is equal to, let's say, or actually first we need to define a binary tree object. So we'll say, let's say binary tree, or we'll even be a bit more concise here. We'll say tree is equal to binary tree. And in this argument, we're going to put in the initial value of the root. So we'll go ahead and put 1 in there. So we have a tree object now, and what we can do is we can start filling in the nodes, the left and right children of this particular root. So what we can do is we can say tree.root.left is equal to node of 2. So what this is going to do is we're going to start off with our root node here. So 1 is the root of the tree. And then what we're doing is we're creating, let's see if I can get the right slash. So we're creating a left child of this root node, and we're setting the value of that equal to 2. So we can also create a right child of the root node. We can say tree.root.right is equal to node, oops, didn't mean to do that, is equal to node of 3. So here what we can do is we're going to define the right child to this thing. We're going to set that equal to a value of 3. And we can keep going. So we can say tree.root.left is equal to node, let's say a 4. So what that's going to do is it's going to define, let's get some more space here. Move this over here, move this over here. A bit more space there. So let's see, let's just space these apart appropriately. So 2 is left child of the root 1, and then 2 is going to have a child now. So 2 is going to have a left child. Let's see here, move this down here. So 2 is going to have a left child of 4. And then we can also define, let's say, tree.root.left.right is equal to node of 5. So what I'm doing here is I'm saying that tree.root.left, so here we're here, .right, so right will be the right node of, not necessary, but it gives us a little more data to play with. So now to actually in a dimensional data structure like an array, of defining each of those traversals, then once you define 1, it's pretty straightforward to define the remaining 2. So we'll
Hello, fellow program data structure in 9 hours, and we want to perform 2 operations. The first one is we want to compute prefix sums. And the second one is we want to add a value to an element. So for instance, we want to compute the sum of the first 5 numbers. The first 5 numbers are 1, 7, 3, 0, 5, and the sum is 16. Now we want to add the value 5 to position 4. So we take the 0 and update it to 5. By the way, I use 1 indexed notation here. So the first element in the array is at index 1. In most programming languages, the index of the first element is usually 0. But there is a really cool trick that you can do when you start with 1. I'll tell you at the end how you can have the best of both worlds. And then we want to compute the sum of the first 7 numbers. The first 7 numbers are 1, 7, 3, 5, 5, 8, 3. Notice that we don't have the 0 anymore. The 0 is now a 5. And the sum of these 7 numbers is 32. Okay, what are possible approaches to this problem? If we have a lot of add operations we want to perform, then
Hello friends, my like this is why I use Fenwick Tree. What are the other alternate solutions if we did not use Fenwick?
Plans inevitably change. With roadmaps in Jira software, quickly adapt.
Welcome to StableSort. In this episode, we're going to discuss a data structure called Fenwick Tree, also known as binary index tree. We'll develop simple visual explanations of how it works, and then dive into to learn how to implement it and also efficiently populate it with data.